Hello class, hope all is well. In this video, we're going to be looking at polar coordinates. Um, so up until now, the coordinate system we've used is the rectangular coordinate system, like x comma y, and it's one you've used probably most of your math education. It turns out though that there are other coordinate systems out there, and this is the most natural one to learn here in pre-calculus because we've seen so much trigonometry. Um, so hopefully this won't take too long. It'll be a pretty short video. Um, just kind of give an introduction to polar coordinates, and we're going to kind of discover them here. So recall, so what I want you to recall here is your rectangular coordinate system. So we have a point in the xy plane. Here's xy, and here's the point here. We'll call it x1, comma y1. The name really doesn't matter. What matters is that it is a point in the xy plane. Given any point, this is how we graph it, right? So this is how far or where are we at on the x-axis, this x1 value. And so we go over until we're at the x sub 1 value. And the same goes for the y1 here. We go up y1 units, whatever those units are. Okay, and so where these things intersect, and we have these kind of, you want to imagine these lines here, where these things intersect is the point, x1, comma, y1. Now this is, again, very standard. We've known this for a long time. But with trig, we can represent this point in a different way, the point in space in a different way using angles and a radius. And why would we want to do this? Well, it turns out in calculus, there are certain problems that occur where you can only solve them by changing your coordinate system. It has to do with integrals and things like that. And so let's kind of discover how we can represent this point x1, comma y1 as a point in polar coordinates and how we might do that. Okay, so I'm going to erase this here and give us a little bigger picture to make it easier to see what's going on. We're going to restrict for now to the first quadrant just to make our lives a little easier. Again, it's just an introduction to polar coordinates. So here we are. Here's the x-axis, here's the y-axis. And again, we're only looking at the first quadrant. So I'm going to plot a point here. Again, this is, we're going to call it x1, comma y1 in our rectangular coordinate system. But let's try to maybe convert this to something that is polar. And what do I mean by that? Let's see. So in trig so far, we always have a radius of some sort, and we have a radian or an angle measurement of some sort. So if we look at this point here, and well, let's try connecting the origin to this point with a line. So we're going to connect, if I can draw a straight line, we're going to connect the origin to this point with a straight line. Just pretend that's straight. This has a distance, right? We'll call it r. So there's r. Now, what we can also do here is notice this radius. You want to imagine this radius laying down on the x-axis, and we slowly we raise it up. Okay, it's attached at the origin, but we're going to raise it up. And as it goes along, if we attach it here and we move this radius along, we're going to carve out a circle, right? And you can kind of think about it. If we have a point, let's say it's another point over here, x2, comma y2, it makes, intuitively, it makes sense that we should be able to find a radius, right, for any point, and that radius should be determined, not necessarily uniquely because we need the angle measurement, and even then it's not unique. We'll see that in a second. But nonetheless, we still should be able to find a radius that connects the origin to that point. We'll call it R2 just for that. just for the heck of it. But more importantly here, we have this radius, and what if, erase this, what if we were able to measure this angle here? We'll call it theta, because that's what we call angles in pre-cal. What if we can measure that angle? Well, surely we can, right? Like, we're okay with that. If we were given that angle, we would know what it would look like because we've worked with it so much up until now. So it seems like we have some radius and some angle, and intuitively, this sort of determines where this this rectangular, at least this point in rectangular coordinates is, and it actually does. Up to, obviously, I could take this theta, go around 2 pi again, and I'm back to where I was, right? And I could do that an infinite number of times. So we don't have uniqueness necessarily, but it makes sense, right? Like we can still use this to express a point in polar coordinates like this. Okay. So let's kind of let's try to see how could we take a point like this and maybe convert it to polar coordinates. Okay. So give that a thought for a second. Okay, hopefully we've given this some thought. Let's try converting. Let's say we're given this rectangular coordinate here. How might we convert this to something polar? And when I say that, how can we write this in polar where we have just, I mean, it's very similar polar coordinates to rectangular coordinates. We say r, well, here we have r1, comma, theta, right? So how do we convert our rectangular coordinate to a polar coordinate? Well, if you look here, in trig and in pre-cal, our goal really is to look for right triangles everywhere we can. Notice this length here, right, where we have a right triangle, this length here is x1. This length here is y1, okay? And we already know some things from trig and actually from algebra. We know that x squared, so x1 squared in this case, plus y1 squared is going to be r1 squared, right? And so if we want to figure out, right, we want to go from some rectangular coordinate to a polar coordinate, we need to know what r1 is and we need to know what theta is. So how do we figure that out? Well, we could first use this, right? So we have an equation in x, y, and r here, right? X and y from the rectangular coordinate system, and then r from the polar. Well, if we just solve for r1 here, all right, we can do square root both sides, plus or minus. Here we're just going to look at the plus because we have some positive radius here. So r1 is just the positive square root of x squared plus y squared, or in this case x1 squared plus y1 squared. Okay? So we actually were able to already determine what r1 is, which is kind of nice. But with that being said, how do we figure out this angle measurement here, right? How do we figure that out? Well, let's try trig, right? Trig, I mean, that's the whole point here, is to use what we know about trigonometry and pre-calculus. So let's look at sine of theta here, okay? So sine of theta. Again, we kind of just play around here, like we're just trying to discover this. So let's just play around with some of the trig functions we know. Sine of theta is opposite over hypotenuse, so y1 over r1. What about cosine, right? Cosine of theta, of that same theta, is adjacent over hypotenuse. So x1 over r1 okay. Let's look at tangent. Tangent of theta is opposite over adjacent, y1 over x1. Okay, and so we've looked at our main trig functions here. I mean, we're ignoring the arc ones for a moment. We've used our trig functions here, and we've kind of related all of these values with each other. But only one of these has all the information we need to figure out what theta is. So remember, we already know, we're assuming we know what x1 is, right? We're converting a rectangular coordinate to a polar coordinate. We already know what x1 is. We already know what y1 is. And we want to know what theta is. Well, the only function here that has x1 and y1 in it, and also theta, is tangent. Okay, so let's use this real quick. Let me come over here. I'm going to come right here. We're trying to find theta, so let's solve for theta using our trig. So we're going to solve for theta. So we have tangent of theta equals y1 over x1. Okay, that's just from down there. That's what we discovered a second ago. And now we have our arc functions, right? So we can do arctangent of theta equals arctangent of y1 over x1. Again, these are they're inverse functions. They undo each other. And so we're left with theta here. Theta is arctangent of y1 over x1. And so there we go. We were able to figure out over here, we figured out what the radius was given a rectangular coordinate. And over here, we're actually able to figure out theta given this rectangular coordinate. Now, again, you have to be careful. You have to remember, okay, where's my rectangular coordinate? Because in trig, you have these values pop up all over the place. If you remember some of the times, you'll be solving an equation and you'll end up with two possible thetas, and then you have to look at what scenario is going on, right? Like, where's the point live? Here in this case, we're talking about the first quadrant, so we're going to ask what theta makes sense for being in the first quadrant. Again, we'll look at examples about that in just a second. But yeah, so if we look here, this is really just, it's not really, I'll say that instead. R1 is just the square root x1 squared plus y1 squared. And theta is just the arctangent of y1 and x1. So theta is just the arctangent of y1 over x1. And again, we have to be careful because theta changes depending on where your point lies. So we found a way to convert a rectangular coordinate into a polar coordinate.